Hello, this is Emad Mirabi. This is a sample of my online teaching sessions. Okay, let's go. Isolated system. What is an isolated system? A system that doesn't change matter or energy, including heat or work, with its surrounding, is an isolated system. So, in an isolated system, we have no exchange of matter and no exchange of energy. Okay. An ideal thermos bottle is an example of isolated system. Perfect insulation, there is perfect insulation. So in an isolated system, Q is 0, W is 0 because no energy is transferred, and of course there's no leakage. No matter is allowed to go in and go out. So perfect insulation means Q is 0. Another example of isolated system is a calorimeter. In calorimeter, we learned that we put a hot object inside water inside the calorimeter, and then we measure the final temperature. So when you close the calorimeter, it's an isolated system because after we close the calorimeter, there's no exchange of matter and there's no exchange of energy, of course. The universe in thermodynamic terms is another example of isolated system. What is a closed system? A system that can exchange energy. So heat and work can be present here, but no matter with its surrounding. It's a closed system. So closed system is what we worked on in the previous sessions of thermodynamics. For example, we could have a sealed rigid box here. It can be insulated or not insulated, so you can give heat to this rigid box. So Q can be present. Q is positive here if we giving heat, and of course in this case we have no work. It could be a cylinder with a piston here, so you have some gas confined in here. So in this system there's no leakage of gas or the material. We have no material exchange. Okay, but heat exchange or energy exchange is allowed. Okay, a sealed rigid container of gas heated from the outside is an example of closed system. A piston cylinder device with no leak is another example of closed system. Okay. Open system. So in open system can exchange both energy and matter with its surrounding. For example, a boiling pot of water without a lid, steam escapes and heat flows. So this is an example of an open system. A steam escapes, so matter is exchanging. Heat flows. We're giving heat to keep the water boiling. Okay, a human body exchange heat, work, and matter like food and oxygen. Food and oxygen are matters which we take, and of course we exchange heat. We do some work. So human body is an open system. Okay, now let's define what is entropy. Quantitatively or qualitatively, I think it should be written here quantitative. Here this must be quantitative. Now qualitative explanation of entropy is a measure of disorder, randomness, or the number of possible microscopic arrangements in a system. Systems tend to evolve toward greater disorder or higher entropy. Now, quantitative definition of entropy is integral of dq over temperature. This is the absolute temperature, of course. We integrate this from the initial state to final state. Okay, I will explain how to calculate the entropy change in the upcoming slides. In isothermal processes, so when we are taking the integral, this is integral of dq over t when temperature is constant. So temperature comes out of the integral, and then you can integrate dq. So integral of dq will be q. So q over t will be delta S in isothermal processes. When temperature change T of a system is small relative to the temperature in Kelvin before and after the process, the entropy change can be approximated as, so S final minus S initial is roughly Q over T average. So this time temperature is not constant here, but change is very small with a small amount. So when temperature changes small relative to the Kelvin, for example, assume that temperature goes from 10 degrees Celsius to 20 degrees Celsius. So 10 degrees Celsius is 283 Kelvin. 20 degrees Celsius is 293 Kelvin. So it's not a great change in absolute temperature, so we can take the average temperature here and use the same formula. Okay. Some examples of entropy increase are melting of ice. In the melting of ice, of course, heat is needed. Q is positive. Temperature is constant. Therefore, delta S is positive. Ice, disordered crystal melts to liquid water, more disordered. So we'll have more disorder here. Diffusion is an example of entropy increase again. Perfume molecules spread throughout the room. So entropy increases here because disorder increases. Every kind of diffusion is the same thing. For example, if we drop an ink into a large vessel of water, again the same is applicable, and entropy change is we have entropy increase, or entropy change is positive. Second law of thermodynamics, this is entropy statement. The entropy in an isolated system never decreases. It either increases or remains constant. So delta S of an isolated system is greater than or equal to 0. For example, when you have a calorimeter like this, and of course it is isolated, you have some water inside and you put a hot stone in it, they reach equilibrium from the moment you close the lid of this calorimeter until it reaches equilibrium, or whenever. It is an isolated system. Inside the isolated system, we can say for sure delta S of this system is greater than or equal to 0. Equality holds for reversible processes, and inequality holds for irreversible processes or spontaneous processes. We'll talk about what is reversible process and what is irreversible process in the upcoming slides, of course. What are the implications? Heat flows spontaneously from hot to cold, not the other way. I'll show this one quantitatively. That's why positive change of delta S, positive change of entropy, will lead to heat flow, spontaneous heat flow from hot object to cold object. Why? And why the heat will not flow from cold to hot? Why not? No process is 100% efficient. Some energy always disperses as heat. So this is just like the heat engine statement of the second law of thermodynamics. Okay, what is a reversible process? A reversible process is an idealized process that can be reversed at any point without leaving any net change in either the system or the surroundings. In other words, if you run the process backward, both the system and environment return to their exact original states with no energy dissipated as heat, friction, or other losses. It requires the process to occur infinitely slowly so that the system is always in thermodynamic equilibrium, or mechanical, thermal, and chemical equilibrium. Here's an example. How to imitate a reversible process. For example, we have some gas here. This is the initial state. This is the final state. Here we see that it's expanded. Figure shows how to produce a reversible isothermal expansion. Why it is isothermal? Because we have a thermal reservoir here and we have insulation here. So the gas will be in contact with the reservoir, so it keeps the temperature will remain constant. So it's an isothermal expansion. We confine the gas to an insulated cylinder that rests on a thermal reservoir maintained at the temperature T. We begin by placing just enough lead shots on the movable piston. So we have a lot of very tiny spherical lead pieces here. It is also called lead shot or metallic shot. We begin by placing just enough, by removing this shot slowly, piece by piece. Expansion occurs very slowly. This is very close to isothermal expansion. So if we take these spherical pieces one by one, the weight on this gas decreases, so the gas starts to expand, but very gradually. And at the end, when you have taken, when the lead shot decreases, you will have gas expanded like this. If you put the lead shot one by one slowly back into this, we'll have a reversible isothermal compression. So going back from this state to this state, we need to add these lead shots very slowly, piece by piece, because the process is happening very slowly. This is how we imitate, or we can get close to a reversible process. Key characteristics of a reversible process. It is quasi-static. The process happens infinitely slowly, so the system passes through a continuous sequence of equilibrium states. There is no dissipation, no friction, no turbulence, no unrestrained expansion, electric resistance, or inelastic deformation. We don't have any of these. System and surrounding returnable. So both system and surrounding can be restored to their initial states. Entropy for a reversible process in an isolated system is 0, which means entropy remains constant. Delta S is 0. So for an isolated system, we know that Q is 0, there is no heat exchange, and when we have a reversible process that there is no heat exchange in it, we can say that it is an isentropic process. An isentropic process is a process that entropy is constant. Iso means the same, entropy is clear, so isentropic process is a process where entropy remains constant. But entropy can be transferred between system and surrounding without net increase. So we can say generally that For a reversible adiabatic system, it is isentropic. Okay, these are key characteristics of a reversible process. Isothermal reversible expansion or compression of an ideal gas is an example of a reversible process. We showed how to imitate this process by adding by consuming or putting a lead shot and adding those little spherical pieces one by one or slowly. We can have compression, and by taking those lead shots we can have expansion done infinitely slowly with a piston in contact with a thermal reservoir. A thermal reservoir is needed because we need the temperature to be constant. Okay, reversible heat transfer across an infinitesimal temperature difference. So to have a reversible heat transfer, you need to keep temperature difference very small, very small. If you expose the system to a large temperature difference, it is an irreversible process then. Okay. Phase change, melting, boiling, freezing, occurring at constant temperature and pressure very slowly. This is another example of reversible process. Example of irreversible processes. Most natural processes are irreversible. Free expansion of gas into volume. Heat flow from hot object to cold object when there is a considerable temperature difference, of course. Frictional work, another example of irreversible process. Sudden compression or expansion, all of them are examples of irreversible processes. As said, most natural processes are irreversible. How to calculate entropy change? To find the entropy change for an irreversible process, replace that process with a reversible process that connects the same initial and final state. Because, if we want to go, for example, consider this is a PV diagram. We want to go from this state to this state. This is initial state. This is final state. Assume that they lie on an isothermal curve. So if it expands very quickly, it is an irreversible process. But only initial state and final state is important for us, which means, entropy is a state function. Entropy is a state function which depends on only the initial and final state. So delta S, it depends only on the initial and final state. No matter how you calculate it. It doesn't matter if we know the initial state is this one and the final state is this one, no matter how we calculate it. For example, we can go through this path or this path or this path, whatever we take, whatever we go, whatever way we go, delta S will be the same. So we choose to do the calculation based on an irreversible process, which happens very gradually. Okay. Can a process have an entropy decrease or negative delta S? Yes. The answer is yes. Let me tell you how. For example, in the case that we just saw in the isothermal expansion and compression, here is the gas confined in a piston, in a cylinder with a piston. So if you apply some work, consider this to be isothermal. So when we have isothermal, temperature is constant, and delta T is 0, delta U is 0. So based on the first law of thermodynamics, we can say that Q is equal to W. So when both of them are negative, when we apply some work, external work, we have negative W, and then Q is negative. So if it is surrounded by a temperature reservoir, temperature remains constant, and if we apply some work, the whole work will be given as Q. So delta S can be calculated as Q over T, because T temperature is constant, it is positive, Q is negative, and therefore delta S is negative for this process. So let me say in isothermal, we can say in isothermal compression, this is the case. Let's consider isothermal reversible compression, so that we make sure that the calculation is like this, and everything will be fine. Okay. Let me tell you, does it violate the second law of thermodynamics? No, because the second law of thermodynamics would say that delta S is in an isolated system is greater than or equal to 0. Is it an isolated system? Of course not, because there's heat, and there is heat and work exchanging here. It's a closed system, but it's not an isolated system. So in an isolated system, delta S is always positive or 0, or greater than or equal to 0. But here it is not an isolated system. Okay, so it doesn't violate the second law of thermodynamics. Another example. Determine the sign of delta S in each process. Okay, here's an example of determining what is the sign of delta S, if disorder is getting increased or it is going through more order. Ice melting at 0 degrees Celsius. So melting, as we learned, in melting delta S is positive. Water freezing at 0 degrees Celsius. Here delta S is negative. We can calculate, of course, delta S, because these processes are isothermal processes. T is constant, so in isothermal processes delta S is equal to Q over T. And when Q is positive, because absolute temperature is always positive, when Q is positive, delta S is positive, and when Q is negative, delta S is negative here. Boiling water at 100 degrees Celsius. Again, delta S is positive because heat is getting absorbed by the system. Condensation of steam. Delta S is negative here because heat is rejected from the system. Free expansion of ideal gas into vacuum. We have a formula that says delta S is equal to NCV ln of T final over T initial plus NR ln of V final over V initial. We will learn this formula at the end of this session. Delta S of ideal gases, are related to with this formula. Free expansion of ideal gases is usually isothermal, so this term goes away, which means T final over T initial is 1, ln of 1 is 0, so only ln of V final over V initial will remain. Because we have expansion here, the volume expands, this is positive, so ln of a positive number is, this is greater than 1, ln of a number which is greater than 1 is positive, so therefore here delta S is positive. It is clear that in expansion we have more disorder. vice versa. In compression, we have more the order. Okay. Compression of an ideal gas, isothermal and reversible. Free expansion of ideal gas into vacuum, yes. Delta S in this process is, of course, positive, because I told you that this term is positive. Now, number 6, compression of an ideal gas, isothermal and reversible. So here, as I told you, this is isothermal because so temperature goes away, and this fraction is less than 1, so ln of a number less than 1 is negative. So number 6, delta S, will be found to be negative. Number 7, heat transfer into a system at constant T. At constant T, this formula applies. So heat transfer into a system, therefore delta S is positive. Heat leaving a system at constant T. Here Q is negative, therefore delta S is negative. And of course temperature is constant, so we can apply this formula. Adiabatic reversible expansion or compression. We say that adiabatic reversible is an isentropic process. So even if we want to integrate this formula, in every step dq is 0 because it is adiabatic system, so dq is 0 in every step, therefore delta S is 0. So there is no change in entropy in this process. Mixing two different ideal gases. Delta S is positive here because we'll experience more disorder here. Mixing of different ideal gases causes entropy to increase. Okay. Another example. Half mole sample of an ideal gas absorbs 1000 joule of heat reversibly at a constant temperature of 300 Kelvin. Find the change in entropy of the gas. So because it is happening at constant temperature, again the formula can be written as Q over T. The heat is absorbed by the system, so Q is positive, and the temperature is given to be in absolute scale, so it is 10 over 3 or roughly 3.3 joule per Kelvin. The unit of entropy is joule per Kelvin, of course, because heat, the SI unit of heat is joule, the SI unit of temperature is Kelvin. Okay, this is the entropy change of this gas. Another problem. A scientist places a block of hot metal at 400 Kelvin, which is roughly 127 degrees Celsius, into 1 kilogram of water at 300 Kelvin, which is roughly 27 degrees Celsius. Eventually, the system reaches thermal equilibrium at 350 Kelvin. Find the entropy change of the metal and entropy change of the water. We know that it's just like a calorimeter. In a calorimeter, we put a hot metal into water, which is inside the calorimeter initially, and then after some time, we measure the temperature when it is at equilibrium. So we have an isolated system here. So we have an isolated system just like a calorimeter here. Some water here, and a hot stone is placed inside. Now, because it is an isolated, we know that the Q gained by the stone is equal to the Q gained by water is equal to Q lost by the stone. So the MC delta T of the stone is equal to MC delta T of the water. Delta T in both cases are the same because the mean temperature, the final temperature is the mean. So the delta T in both cases are 50, so we can understand that the magnitude of M1C1, which is the heat capacity, is the same in both cases. Here's the first point. So we understand, because it is, you know, we expected the initial temperature of the stone is 400. The initial temperature of water is 300. We expected the equilibrium temperature to be something between 300 and 400. But when it is exactly 350, we understand that heat capacity of them must be equal to each other. Not a specific heat capacity. Heat capacity. Okay. Now, how to calculate entropy change? Entropy change is calculated like this. Delta S is equal to integral of dq over t. So can I replace dq with mc dt? Yes. So then mc is constant, which is the heat capacity, and integral of dt over t. For example, if I want to calculate it for water, it will be 1 kilogram of water. The heat capacity of water is 4,200 joule per kilogram degree Celsius. Multiplied by 1 kilogram, this goes away. And of course, ln of T final over T initial, because integral of dt over t will be ln, and replacing the t final and t initial will have this formula. So 1 times 4,200 times ln of 2. Is it ln of 2? No. What is the final temperature? 350. The initial temperature of water is 300. So let me do the calculation here. 350 divided by 300, and take the natural logarithm and then multiply it by 4,200. I'll get 647 roughly. 647. This is delta S of water. This is delta S of water. What about delta S of the stone? It is the same, so the only thing that changes is, I told you already that MC is the same for water and the stone, so heat capacity is the same. So let me put 4,200. The temperature, final temperature is 350, but initial temperature is 400 here. So let me do the calculation. 350 divided by 400 is 0.875. Natural logarithm is a negative number, and this time it gives negative 560. Negative 560. Now, delta S of the whole system, delta S of, let me write delta S total here. Delta S of the total system, which is an isolated system, is found to be positive here, which is around 40 here, the efficiency to 600, and 47 here. It will be 87 joule per Kelvin. Here the unit is joule per Kelvin, of course, and here is again joule per Kelvin. So delta S, total delta S, or delta S of the isolated system, is positive, and this is in agreement with a second law of thermodynamics, which says in an isolated system the total entropy change must be positive for spontaneous, and delta S total will be 0 in irreversible processes.